Okay, so last time what I did was a few examples about how to solve the simplex method uh, using this matrix notation, which I do find is the most convenient once you get used to it, uh, because then it doesn't feel that different from like what you do with Gauss-Jordan, like when you start row reducing a matrix. That's essentially what you're doing in this case, but you're not trying to find the row reduced echelon form. That's the only difference. Oops, let me turn this upside down. No, it's fine. Um, what I wanted to this so today I'll continue doing these examples where we solve the linear problems using the matrices. But what I wanted to do was discuss uh, two kind of like extreme cases. So kind of like in the majority of the cases, everything works out nicely. There are two situations where things could go wrong. And one depends on what you mean by going wrong. So that's the first case, which I'll start with today, is when there's no max, just because like the max is infinity. In the sense like you can find like larger and larger values for the function you're maximizing. So that's when happens when the region is unbounded. So that's like the first case I was going to like address. So I'll show you how does that look and how does is that reflected in when you're trying to do the matrix approach. And the other case that we have to discuss today is like the degeneracy, like the degenerate case. I'll show you what can go wrong there as well. Okay, so let's start with the unbounded regions. So let's start with like an easy problem. Let's say that you want to find the max of x1, just like x1, and then the conditions are the usual ones. So subject to um, two variables being non-negative, and then the interesting inequalities are these two. Oh, sorry, less or equal to 2. Okay, so if you want, like in this case, it's kind of like useful to see graphically how that looks so that you kind of like can see why it is a unbounded region. So let me start. I'll switch to like more like traditional notation to find the graph of this region. So again, like the first two conditions, like just tells you that you're working on the first quadrant. Okay. So how can I write this like in more traditional form? That would be x minus y equals 1. Sorry, less or equal to 1, right? So you can say that x minus 1 is less or equal to y. Okay, so how do you plot that? So again, like you can do like the equality first, like that would be the equation of a line. It's decreasing line, increasing line because it's positive slope. So oops, this is roughly how that line looks like. So this is 1, comma 0. Okay. And then what is the other inequality? If you go to the traditional notation, is minus x plus y less or equal to 2, or y is less or equal to 2 plus x. Okay. And also this is a line which is increasing. The intercept is at 2, so you would get something like this. And this is the line y equals 2 plus x. Okay. So if you can see these two lines, they are parallel because they have the same slope, right? So because the region is only in the first quadrant, the region of interest, in this case, if you kind of like work out the inequalities, you kind of get like, it's, you know, it's almost like a strip with like an extra part, right? Like, it's like the stuff between these two lines in the first quadrant. And with this like extra region. Okay, but like hopefully it is plausible that, because the lines do not like the lines are parallel, so they never intersect. So there is really no way to close off this region, if you know what I mean. So like this region goes on forever. Like it's always between this, like, you have this between the lines. Yeah.
Why do we take between them as a region?
Oh, because of like the inequalities per se, right? Because
Don't we need to take the like below red line? Or because it's less than, right?
Let's see. Did I mess it up? Let me see. Let me see. Okay. So for the red one, y has to be above, right? For the red one, y has to be above x minus one, right? So for example, if you like, oops, let me just do, you know, like for example, here's like the point 1, 1, right? Uh, that point satisfies this inequality, right? Because
you just placed it right there.
yeah. And the other one is y less or equal to 2 plus x, so that one is below the line, yeah. So it's above the red line and below the, yeah, no, that can always, be confusing. So that's why I always, I'm like, do the equation first and then like, try to find that out. But again, my point here to notice is like that this region goes on forever, right? And this is what you call unbounded, in the sense that it is okay. Unbounded means that it is not contained inside like any finite square. That's one way you could define it. So like, let's just say that this region is unbounded. And by that, I just mean that it is not inside any finite square. Well, any square is finite, but it's not inside as any square at any square. So there's no square that you can draw that contains the entire region. You could do it with spheres, like it doesn't have to be a square. I just mean like there's no like, finite container you can place it inside of. Like it's very intuitive, like, once you see a picture, it's very intuitive. Now, if you look at this optimization problem, like just from the graph, you don't expect there to be a maximum, because what are you trying to maximize? You're trying to maximize the x coordinate, right? But the x coordinate keeps increasing. Like, all these points, like, I don't know if you see my picture, all these points are moving away and they're increasing their x coordinates. So there cannot be, like, you kind of expect from the picture that there's no solution to this maximization problem, because the x is unbounded, like the values for x, they just grow forever. So we expect there to be no solution to this problem, right? Or if you want, you can say that the solution is infinity, but like we only interested in finite solutions, so we would say that there's no solution if like the solution is infinity. But I would say we expect the max to be infinity, or in other words, no solution. No finite solution to the maximization problem. Is that okay? Everyone convinced of that, persuaded with that? Okay, this is all nice or fine. What I'm going to show you is like, pretend that you never saw this picture. How would you tell that from from the matrix presentation of the system of inequalities? So what I want to show you is, if you like ignore that you ever saw this, you just don't notice that, and you try to solve this maximization problem. What happens when you apply the simplex method here? Like, where does it break down? So what what happens in terms of the simplex method here. Okay, so again, for the simplex method, what you have to do is turn everything into an equality, right? So I'll write like the inequalities as equalities. For that, I need two slack variables. So I'll put plus x3 equals 1 and negative x1 plus x2 plus x4 equals 2, right? And the other thing I mentioned you, which is convenient when you do this matrix version of the inequalities, is to keep track of the function that you're maximizing. And the name we were given last time to the function you're maximizing was z. So I'll just call z equals x1 in this case, which is kind of like silly because it kind of seems redundant in this situation, but it just, like the optimization function could have been a bit more complicated. And so it would not have been as, like, may not have been as dumb as that. Um, so again, this is kind of like the name for the optimization function. So again, when you read this off, you put the coefficients 1, -1, 1, 0. Then you augment this. Okay, so again, not that you have to write the names of the like the columns what they correspond to, but those are like the variables for each column. Now, what I mentioned, which is useful, I'm sorry, I'm forgetting about the two. So what I mentioned is also useful in this type of problems is again to keep track of the optimization function. So in order to keep track of it, you just put like a horizontal line. That's kind of like as a reminder that you're working with like the last row is not truly like a row of the matrix. It's kind of like when you augment the matrix, right? So where like the last column is kind of like the column of constants. So here, you put the optimization function, which I'll write, like if you look, this equation can be written as negative x1 plus z equals 0. And so I'll do that to extract off the coefficients. So the coefficients would be -1, 0, 0, 0, 1. Okay. And there's no z in the first two equations, so you would get 0 and 0. And this one is equated to 0. Okay. Is that making sense? Questions about that? So far, so good. Okay. And then what the method says, the first step is, you know, of these columns, what the simplex method says is that you choose the column with the largest negative coefficient in the last row, right? So I'll just repeat what you have to do. So choose column, largest negative coefficient in the last row. Oh, in this case, there's only one column with a negative coefficient, right? Which is like the first column, which makes sense because the function was just x1. So that's the only variable that we can increase at the beginning. Okay. So in this case, this is, I'm going to focus on column 1. Right? And for each, okay, and then again, what I do to choose like an entry in this column, what I do is take the ratio between the coefficient, the constant term at the end of the corresponding entry. So for the first one, like the ratio is 1/1, which is 1. And for the second one, the ratio is 2/-1, which is -2, right? And the idea is to choose of these two ratios, you choose the smallest positive ratio, right? So the clear winner in this case, I mean, there was only, you know, it is that one. Okay. So, so okay, like let me stop here to see if there are any questions. So once you have, that's how you will always identify the entry in the matrix that you care about. Okay. And then what was the next step? That you make zeros everywhere else in that column. So every other entry in that column has to be turned into zero. So turn every other entry into a zero. Okay, so how do you do that? You do row operations. So what are the row operations in this case? They would be sorry, it would be row one plus row two into row two, and I'll also do uh row one plus row three into row three. So let's see what happens here. So the only row that stays the same is like the first one. So when you add the coefficients, like you get one plus minus one, 0. Then this one also gives you 0. This one gives you 1. This you gives you 1. This one gives you 0. This one gives you 3. And then the last row becomes when you do the addition, you get 0, -1, 1, 0, 1, and then 1. Is that making sense? So far so good. Questions about this? Okay. And then again, what is happening here, not that you have to kind of be super conscious about it while you're solving the problem, but what is happening here is like that you kind of like are doing like a swapping operation where like you're turning some basic variables into non-basic variables. So here, like, originally, if you want like one way to think about it, let's see. Yeah, so like originally, if you want, you can think of these two as being like the basic variables, and these were like the non-basic variables. And now in this operation, when you do the swapping, like now x1 became a basic variable and x4 continues to be a basic variable. So you swap x1 with x3 basically. That's kind of like what's going on behind closed doors, but you don't have to be super aware of it to kind of like solve the method. It's only at the very end that you kind of like reuse that. Because now when you go to this part of this algorithm, it repeats. So like now you find a column with the lowest, like largest negative coefficient. So now you repeat the algorithm. So in this case, like the only one we can choose um, is the second column, right? So I choose the second column. And again, what happens here is that you had to choose in this column one of these two entries, right? But in order to decide which of the two entries you choose, you look at the ratios. So if you look at the ratios are 1 over -1, which is -1, and then 3 divided by 0, which is infinity. That's one way to think about it. But the condition is to choose the smallest positive ratio. There's no positive ratio here, right? So you had to choose smallest positive ratio. Uh, but there's no positive ratio, right? Like it's either negative or infinity, like the two options. So you're stuck. The algorithm terminates. Okay, so you're done, and that tells you that the solution is unbounded because well, it's actually useful to and this like tells you that there's a solution, subdown solution. It is actually useful to kind of like look at these equations like one more time, like in terms of like the actual variables. If you like, how does this look in terms of like in terms of the equations, just to convince yourself a bit more. If you rewrite this as a system of equations, you get x1 minus x2 plus x3 equals 1. You get x4 plus, sorry, x3 plus x4 equals 3. And then you got like the optimization function is the last row. You get this. So again, like a Z is what you're trying to make as large as possible. And you can kind of see pretty clearly that from this presentation, to make Z as large as possible, you have to make X2 as large as possible, which is why we were focused on column 2. Okay. But then, if you look at this equation, if you look at where is the only equation that where x2 appears? It appears in the first one, right? So a more convenient way to look at this equation is x1 plus x3 equals 1 plus x2, right? Uh, so basically what's going on here, if you notice, it's like, you're trying to constrain how long, you're trying to determine how big can you increase x2, right? But just like imagine that you're making like x2 like 100, you will be able to find like a value, like, the only constraint on x1 and x3 is that they have to be non-negative. Um, so like, you can increase this as much as you want, and these just like adjust their value so that it matches whatever you want x2 to be. You know, there's no like if you look, well, I mean, in principle, like, the basic variable, like the non-basic variables were x3 and what are they? X3 and x2. So even if you set, like, you could have set up x3 equal to 0 here if you like, but even if you set x3 equal to 0, uh, like there is no constraint that appears on x2, because if you make x2 99, then x1 just has to be 100, for example. So like they kind of like match, like they go side by side, so they can be increased uh, without issues. But again, it is a little bit more like, analyzing it directly from the equations can be more confusing. If you just look at it from the matrix, it's just that there's no ratio that you can choose, and then you're done. And that's kind of how like non-degenerate, like unboundedness looks in general. And I guess that's questions about. Okay, so that was like the first type of problem that I had to show you. Um, how these regions look like in general, like when the region is unbounded. The other type of situation I wanted to analyze today was like these degenerate solutions, or the degenerate case. So again, what does degeneracy means? It means that you had a degenerate basic solution. And what did it mean to say that you have a degenerate basic solution? It means that some of the basic variables are set equal to 0, okay? Okay, so let's first so I'll solve this problem in two different ways. And I'll try to show you what the issue can be here. But let's start again, let's start with something where you can do the picture because it's a little bit better to understand what's going on there. So I think this is like a region we had done before, but just to show you how it looks like, let's see. Well, there's not much to draw. So you have to be below the blue line and to the left of the green line, and in the first quadrant. So the region of integration is not oh my God, not integration. The region of like the polyhedron, like the region that satisfies the inequalities, is a triangle. Okay. And if you remember, the idea is that, again, like the basic solutions correspond to the corners, right? So in this case, there should be 3 basic solutions, okay? But the origin, which is a basic solution here, was a degenerate solution. Because geometrically, what it means to be degenerate is that there, in this case, because it's all two-dimensional, because there are more lines, a point, like this is can be confusing. Like, let me see if I can. I don't know if you like probability theory, but so okay, let's start here. Okay, crash course on what it means probably like what it means to be degenerate. So if you have two lines in space, right? Um, like imagine I gave you a bet to make. So the bet is like, give me a hundred, like you give me $100 if the lines intersect, and I give you $100 if the lines do not intersect, right? So that's the bet. So the question is like, if we kind of play like a game at random where we're kind of like just writing equations of the lines, who would win like most of the time, right? Like that's what you could ask. So if you are smart, like you should bet on the lines intersecting, okay? Because for two lines to not intersect, they have to be parallel, right? And being parallel is like a super special condition. They have to have the same slope, right? So if you think like, imagine like, like, how should I say it? What is like, I don't know if the picture will be seen here for like the video recordings, but like in probability theory, there's all these problems that they give you in terms of urns. So like, imagine that you are blindfolded and you have to grab like a number from this bag, which is like the slope bag, and a number from this bag, which is like the intercept line, because a line is y equals mx plus b. If you know m and b, you basically know the line, except like in a stupid case where like the line is completely vertical because there like it has no slope, but I just ignore that for now. So what I'm saying is that, if you're blindfolded, for the lines to be parallel, I have to pick the same ball, like the same slope from the slope back twice, right? Like, and you're choosing the same ball from infinitely many balls because there are infinitely many different slopes, right? So just imagine, like again, this can be made more precise using some notion of probability, which is not important, but just imagine what is the probability that if you are blindfolded, you will choose like the same point twice on the line, that's on the real line, which is like what represents the slope. You should bet basically that that's zero, right? So that is why you would say that generically, the generic situation, like or like kind of like the most likely situation is that two lines in space on the plane are intersecting, right? Because it's really, really special, for the lines um, to be parallel. Okay, so if you choose two lines, right? You have two lines. And here comes like the extra condition. What are the chances, right? What are the chances that if you have a third line you're thinking about, that it happens to pass through that exact point where like the other two lines intersected, right? Okay, so what is the chance? Like, because if you move the line a little bit, like then they do intersect, but they intersect all like at different points. What I'm asking is like, what are the chances that this third line that you chose at random, again, in some sense that you make the choice at random, like you can do it with the Gaussian distribution, like, there are different ways to choose like the probability distribution. That's one way to uh, lay out this more concretely if you wanted to do it like in a statistics example. But what I'm saying is, but you just think about it and you kind of like know what I mean. What are the chances that if you draw a third line, you happen to make it pass through like the point of intersection of these two original lines, and hopefully you kind of think that that's like unlikely, right? And this is what is happening here. Like in the picture, like the original two lines, you can think of them as the x and y axis because they're like appear in the inequalities. So you're having this third line, which is the blue one. Actually, I'll use the same colors. You have this third line, which is the blue one, which also happens to pass through the origin. So the origin in this problem is the intersection for three lines, which is really three lines that appear in the inequalities, right? In the constraint, in the region. And that is like a very special circumstance. So that's what makes it degenerate. So in mathematics, whenever you say that something is degenerate, it's kind of like similar to saying it's like a special condition. It's not something that you so kind of like the opposite of degenerate is generic. So when you say something is generic, it happens in general, right? Like it's not special, so degenerate, so it doesn't have like any moral connotations, like kind of weird how the name degenerate became like how like there must be like a history of why the word kind of got used like as an insult and also like in this situation, but because like with irrational and other things there's kind of like a relation, but I'm just saying like it is called degenerate because it's not generic, and because in general or generically you expect three lines to intersect at distinct points and not pass through exactly the same point. Okay, and again you can kind of like do this in more like fancy terminology if you like probability theory, but like it's kind of like like a rule of thumb. That's also, kind of like give you like a similar example, which is kind of cute from linear algebra. If you have like, well, a 2 by 2 matrix, it doesn't have to be a 2 by 2 matrix, but if you have a 2 by 2 matrix, a matrix has an inverse if its determinant is not zero, right? So in general, most matrices have an inverse, because to not have an inverse, your determinant must be exactly the number 0. So you have to choose 4 numbers and arrange them in such a way that these two products and their difference adds up to 0, right? And that is like very hard to pin down. So in general, like again, like if you know nothing about the matrix, the overwhelming condition is that like the matrix will have an inverse. So having an inverse is kind of like the generic condition because that only requires a determinant to not be 0. But it's very special to have determinant 0. And then that's kind of like the degenerate case. So not having an inverse is kind of like degenerate. And there are many, it's kind of like fun to then think about what is the generic or not in mathematics. Like that's kind of like an important question to ask because it does have like, you know, important consequences for other things. Okay, well, that was just a detour that tells you geometrically, you know, where the degeneracy comes in here. So now I'm going to show you how that reflects in the simplex method. Okay, so how does the degeneracy looks, and I'll say this here because it's like intersection of 3 lines. Okay, so how does uh, the degenerate situation look from the matrix perspective? So again, first you add slack variables to the inequalities. So the inequalities, I mean, if you have them, I'll copy paste them so that it's easier for you to see what they were. But if you add inequalities for the last two, you get minus x1 plus x2 plus x3 equals 0. And then you get x1 plus x4 equals 2. And again, it's convenient to call like the optimization function z. So I'll call that z equals x2, which is the same as saying that, or minus x2 plus z equals 0. So So the equations are this one, this one, this one, and this one. We have 3 equations here. So in the matrix perspective, you get minus 1, 1, 1, 0. Again, I'll put the variables. I think that's useful at the beginning when you're getting used to this. You don't need to, but you know. There's no z in the first equation. Then you get 1, 0, 0, 1, 0. And then the last row, again, is not a row of the matrix. It's just like the row that keeps track of the optimization function. So it would be 0, -1, 0, 0, 1, 0. Okay, so let's try to start here. Okay, so again, when you do this, okay, what's happening in here is that if you start trying to do the simplex method, you start with the column that has the largest negative coefficient. In this case, there's only one choice, so let's start with the second column. Okay. And now there's already something funny that's going to happen here, which probably you have noticed, because if you look at so again, you have to choose, you have to choose by looking at the ratios, right? So here, like, it also, okay, so it does look like uh odd in the same sense, like, because here we do like have a similar problem to what we had before, because you are trying to find you know, the smallest positive, you know, you're trying to find the smallest positive ratio, but there doesn't seem anything to choose from, right? So, okay, so here's like the first issue right here. Okay, but okay, and that is true, but here's the difference with what's happening with the previous case, because in the previous case, or maybe I should say it this way, what happens, I don't know if you remember this, like when we were talking about degeneracy, what occurs when you have a degenerate solution, uh, when you have a degenerate solution, there are multiple bases that correspond to that same degenerate solution. That's something I had mentioned before, if you remember when we talked about like degenerate solutions. So the difference here is like, because this is degenerate, there there can be more than one basis that corresponds to the same basic solution. So it's kind of useful to, it's kind of useful to think about, like, oh, actually, Right. Why am I? That's just fine. Oh, okay, right. So let me explain it in let's say design. Let me okay. Actually, yeah, this is fine, but uh, let me take it back. Like I'll explain it in a better way. Uh, because otherwise, like it will be a bit confusing what's going on. And then I'll show you like a way that like kind of like avoids this issue. But actually it does like the matrix notation. I mean, I'll switch it to matrix notation in a moment, but let me say it first from the system of equations before so that you know, everything is a little bit more clear there. So usually, okay, maybe this is actually like the confusing part. So if you have you know, what is correct when you have when you start the algorithm, you need to choose a choice of basis, right? So in this case, a choice of basis could have been x3 and x4. Okay, let's see. Let me check if I did it here. Let me check my notes if I, yes. Oh, right. I guess so. Like right. No, that's fine. Yeah. Well, so maybe I should have erased this, but like, right, to start the algorithm, we need a choice of basis. So we need a choice of basis. Okay, what was the choice of basis? It was like in a 2 by 2 matrix, which is inverted. So for example, you could have done this, okay? So here, like you could have chosen like columns 3 and columns 4 as the basic variables as the choice of basis, which means that x1, x2 are not non-basic variables. Okay. And so if you were doing it how I had explained it at the very beginning, like before I gave you the matrix notation, the idea to do it that way is that you write like the basic variables in terms of the non-basic variables. So this would be x1 minus x2, and then x4 equals 2 minus x1, and z equals x2. Okay. So again, like the idea here is that these are basic and these are non-basic. Okay. And and then you do want the function to be given in terms of the non-basic variable, so that's good. Okay. And then right, if you're trying like it's just easier to explain it first, like in this format, and then I'll go back to the matrix stuff. If you try to how so what can you do next here? You have to increase x2 as much as possible, right? So x2, right? Like if you increase x2 as much as possible, then like there's only one equation in which x2 appears. So the only way to increase x2 here, right, is by by like from the first equation. So essentially what you have to do is swap x2 with x3 as the basic variable. So again, like originally x2 or x1 are set equal to 0. But if you try to increase try to increase you try to increase x2 while keeping x1 equal to 0. So if you put x1 equals 0 for the time being, you have x3 equals minus x2, and then you get you get x4 equals 2. Okay. And this is kind of like the weird thing because, and that's like actually where the degeneracy is happening, but it's a little bit easier to see here because you cannot increase like x if you try to increase x2 a little bit, right? This is why it's confusing, and this is why degeneracy is a bit hard to explain. But if you try to increase x2 a little bit, right, that immediately makes x3 negative, right? Is that making sense? Okay, so really, really, you cannot increase x2 without messing up x3, right? That's the problem that we have here. So the kind of like the idea is that x2 still needs to be set equal to 0. So x2 needs to be remain to 0. And so essentially the only thing you can do here is kind of like swap the roles of the variables, but there's not much like but you cannot like kind of give a different value to x2. So the idea is that x2 can be increased since it would make x3 negative. So we keep x2 equal to 0, but, and this is like important thing, just we change our minds on which of the two variables is basic. So the idea is we still think of x2 as becoming a basic variable while x3 becomes non-basic, but we turn into a basic variable. So by the way, this is not how we will solve degeneracy in general. I'm just trying to show you what would happen if you try to do it like, in if you try to do it like by brute force. Like there's like kind of like a more clever way. So, but what I'm trying to say is that you know, you kind of swap the roles here. So like you get that x3, x2 is x1 minus x3, and x4 is 2 minus x1. And z, which was x2, becomes x1 minus x3. Okay. Because again, the idea is that the basic variables and the function must always be written in terms of the non-basic variables. So what the issue that's happening here, like, and this is something like that happens, like just to explain the issue that we're having in this situation, the issue, and this is where the degeneracy lies, is that the basic solution, which is 0, 0, 2, comes from two different bases, from which were like columns 4 and which are columns, each are columns 2 and 3, or columns 3 and 4. So, and that's where I was kind of confused like a few minutes ago. So the thing is that, and now I can go back to the matrix thing and fix what I was saying. So just to go back to the matrix, right? So the idea that what was happening is that, basically, if you had like these bases, you know, like these, like there's a basis here, which are these two columns, and there's a basis here, which are these two columns. So these two potential choices give you the same, no, they do give you the same choice of basis. So that is like where like the confusion lies in general, because then like, it's a little like the method is a little bit ambiguous on what to do. So for example, here, the way I was setting it up, like if I had thought about, if I think about like choosing the basis to be 2 and 4. Okay, so if I choose the basis to, like, to be 2 and 4, the problem is that then I do not want, I don't want I don't want the optimization function to be given in terms of like the basic variables. So that's why you cannot have like one here. So you do have to do like row operations first to put a 0 here, which is how you're going to end up with like this system of equations. So essentially, if you do like, what I'm trying to say is that if you do like, for example, minus row 1 plus row 3, Those are my cats, by the way. And sorry, this has been a bit of a mess, but like hopefully the mess shows you why we are not going to solve it this way, because what I'm trying to say is that if I do it like, this system of equations corresponds to this matrix. So like this is kind of like the matrix. So like, let me just put it like here. So the original system of equations was like asterisk. So this was like this matrix. And like the one that you do when you just swap the basic with the non-basic variable would have corresponded to this matrix. Okay. Uh, the So the issue with the degeneracy is that if you see, there was no progress being made because like the function continues being at zero. Like, the value of the optimization function is zero. The idea like of the simplex method is that you always want to increase a little bit like the value of the optimization function in each step. Um, but here there's no progress being made. So it's kind of like feels like you're getting stuck because like there's, you don't change like so like if you notice these coefficients, the value for z didn't change. Okay. So what can happen, and this won't occur in this case, but so what can happen is that if you think about it in terms of like an algorithm, you can end up in a sequence of what they call like a cycles. People call like a cycle where you just are swapping variables, but no progress is being made. So you just kind of like end up like in a loop where you just end up going back and forth between like basic sets of basic variables that you had chosen before. So you can end up in a cycle, so you can in a cycle where the algorithm just like starts like repeating like the steps because like you're not making progress on the value of the function. Okay. Well, fortunately, this doesn't happen in this case. So if you kind of like just do this swapping operation without much, just like, it's not super, and also like it wasn't super clear, like the point of like doing the swapping operation this way, because also like like the ratios were not working properly, so like not like very like the things don't work as like they're supposed to. So I'm like I don't like you almost after today's class, which because I don't have that much time left, you basically can forget about this explanation, and then I'll give you next time the one that we will use in practice, which is to perturb the equations so that you become non-degenerate, and then everything works perfectly. So like this degenerate, I'm just trying to show you what are like the ambiguities that appear in this, like if you do it this way, because don't you do get stuck. So or could get stuck. But if you kind of like continue, if you continue in this case, well, like again, like the only one that is like non like which is negative would be here. But if and in this case, if you do the ratios, you get 2/1, which is good because now you do have like a positive ratio, so you can continue without problems. So you would turn like you would choose this coefficient. Let me just indicate the one that I would choose to make zeros everywhere else. And if you do that, you get okay. And now because every coefficient is positive in the last row, then the algorithm does terminate and the max is 2. So all positive. So terminate. And this is the max, which makes sense because if you go back to the triangle, you see that the max happens like at this vertex, which is at height 2 because of like how the inequalities work. Okay. But there's like this kind of like shady part, there was like this shady, and that's why you saw me struggle because wasn't finding the right way to explain it. But there is like this shady part where it was a bit ambiguous why you do this operation because but that stems from the fact that like in this case when you swap variables there's no progress in the optimization function, so it is not convenient, in practice you don't want to solve the systems of equations this way when there's like a degenerate solution. So again, when it comes to algorithms, there's ways to get around it. And also like this is like a very special circumstance because like again, degeneracy is like very, very low probability in some sense for it to happen. But what I'll show you next time, and you'll see that is way more transparent. And um and this is how we will solve this in general. So like you can forget of what we just did right now because it's not how I want to solve it. I just wanted to kind of give you like a glimpse of what happens. But what we will do next time is that we will solve this. We will remove the degeneracy by perturbing the equations. So what I mean by that is that so this was like the system of equations. And you perturb and then you perturb the equations by adding like an epsilon perturbation to like the constant term. So you would write something like minus x1 plus x2 plus x3 equals epsilon 1, and then x1 plus x4 equals 2 plus epsilon 2. And here you think of epsilon 1 and epsilon 2 as really small numbers. But once you do that, then once you do that, like essentially in terms of the picture, which I think I had shown you before when I had taught about how to perturb things, the thing that happens when you perturb is like the region, like the perturbed region kind of looks like this. And so like the triangle becomes into like a some sort of like quadrilateral. So like like you kind of like separate like the corner where like the intersection happens into two corners. So you create like an extra corner. And then like this will do the trick. And this is what we'll do like in general. So like here, like the gap is what? This is 2 plus epsilon 1, and this is epsilon 2, if I'm not mistaken. No, this is 2 plus epsilon 2, and this is like epsilon 1. Yes. Okay, so I'll show you next time how to do this one. But like I did want to give you like at least a sense of where the difficulty can be when you try to do the simplex method. Like in the degenerate case, it's just that it's more ambiguous because like there's no progress that happens with the function. So like it's more imprecise how to do the swapping. But let's finish here. Again, you can forget this discussion like once we talk about degeneracy next time with this perturbation. That's how I would expect you to do it because you'll see it is non-ambiguous. So like this is kind of like the better way to do it. Okay, so let's stop here. And again, I'll send you tomorrow the grades as an announcement. So